Welcome to our lecture on model identification. Today we're going to cover the second half of the rules around how to draw out and write structural equation models. So model identification is the evaluation of a structural equation model to determine whether it is theoretically possible for the computer to derive a unique set of model parameter estimates. So in other words, can the model actually be empirically derived through M+, whatever software that you're using for the purpose of this class, M+. So can the computer actually derive estimates? Can it get those factor loadings and regression estimates and correlations and covariances that are necessary in order to get results? So there are separate requirements for the structural and measurement portions of your model. So the model where you have the regression paths versus the CFA model. So CFAs have separate requirements around identification. I'm going to go over those pieces at the very end of this lecture. The main purpose of this lecture is to just look at that first part of it, to really look at what it looks like to have an identified model for that part where you actually have the paths going, because that's going to be the more important part for identification. So your models, they can be just identified, over-identified, or under-identified. And as you can see from the colors I used on here, just and over-identified is where you want to be. Under-identified is where you have problems. I'm going to kind of try and help you understand or demonstrate the conceptual understanding of what identification means and how the computer is deriving estimates from your model and how identification causes problems. So under-identification happens when there are more free parameters than there are observations. So parameters are the pieces that are on your structural equation model, and observations consist of the variances and covariances. I'm going to go over this in pretty good detail as we move forward in here. So when you have more free parameters than observations, you are under-identified. So essentially what happens, this is from the Byrne textbook, is that the parameters are subject to arbitrariness, thereby implying that different parameter values define the same model. Such being the case, attainment of consistent estimates for all parameters is not possible, and thus the model cannot be evaluated empirically. Essentially, when you have under-identification, you have negative degrees of freedom. And I want to show through an example of just some basic algebra about what this looks like in structural equation models. So let's take a look at this example. So if you have a plus b equals 6, and I tell you find a and b. Well, what you will find is that you can have a lot of different values for a and b. A can be 5 and b can be 1. That still gets you to 6. A can be 3 and b can be 3. A can be 2 and b can be 4. You have lots of different possible answers for a and b. When you're running your model, a and b, in this example, a and b are your estimates, and 6 is the observation. So 6 could be a bivariate covariance. So in this example here, you can see how you can run your model, and every time you run it, you're going to get different answers. And that's a problem because we don't have a definitive model estimates. So when your model is unidentified, your computer blows up and says, I can't do this because your model is not identified. So go back and check it out. So this is the problem of under-identification. The main problem here is that you have too many parameters so that your computer cannot give you consistent estimates for your model because of the fact that we have here a plus b equals 6, lots of different answers, lots of different possibilities. Just identified is when there are equal parameters to observations. This happens when you have absolutely 0 degrees of freedom. And here is the example we're kind of showing here where you have like if you remember back in algebra, if you did this, where you'd have 2 sets of equations, and then you have to find a and b that works for both sets. In this case, we have 2 observations, 6 and 10, and 2 free parameters, a and b. And when you try and find an a and a b that works for both of these equations, you only have one answer, and that's where a is 4 and b is 2. There are no other possible answers for a and b that still gets you 6 and 10 for both of those equations. So this is a just identified model. There's only one possible solution you can find for your parameters, which are going to be the beta weights and everything else that you're looking for in your analysis. Over-identified happens when you have fewer free parameters than observations. So you have a positive degrees of freedom, so it's more than 0. And the more degrees of freedom you have, the fewer free parameters you have compared to your observations. So this is, in this example, we have 3 possible equations. So we have a plus b equals 6, 2a plus b equals 10, and then 3a plus b equals 12. So in this example, we have 3 observations, 6, 10, and 12, and 2 parameters, a and b. And what you'll actually find is that there isn't a solution you can find that works for all 3 equations at the same time. Rather, there's an answer you can find for the first 2 equations and a different answer you can find for the second 2 equations. And when you look at those 2, you can find an answer that works for all 3 that takes the smallest error, so the smallest squared difference between those 2, between the a's and between the b's, and you'd have a is 3 and b is 3.3333. So 3 1/3. This is similar to what the program is doing when you have fewer free parameters. It's going to find the best answer that has the smallest squared difference. In essence, there's a lot more to it where it's evaluating the errors of the terms and a few other things, but conceptually this is what's happening when you have an over-identified model. So in other words, you have fewer free parameters than observations. So you want your model to either be just identified and over-identified. Now between the 2 of those, between over-identification and just identification, just identified models tend to not be that interesting because you will always have perfect fit for your model because your observations equal parameters. It's always going to be is exactly it. Just identified models also tend to lack parsimony. They tend to have a lot more going on than just what is in your hypotheses and research questions. And especially when you get into more complex models, it just lacks a clear hypothesis of causal relationships because there are too many correlations, too many paths. It's not very clear what you're studying here. So rather, what you want to have is an over-identified model. An over-identified model is going to be parsimonious. It's going to have clear hypotheses. And it's going to be doing what we want to be doing more of, kind of evaluating the fit to the data of our hypotheses, rather than having so many parameters in that it's going to fit the data perfectly. So we want to have an either over-identified or just identified model, but between the 2 of those, over-identified models tend to be more useful because they're more parsimonious. They tend to be much more drawn to the research questions and have very clear hypotheses that you can see in that model. So the next thing we're going to talk about is the rules for identification. So now that you understand under-identified, just identified, over-identified, we're going to go over these rules for identification for the structural model. So that part of the model where you're actually having the paths, so the regression coefficients for each of the models or for each of your manifest variables. So that's what we're going to look at first before we get to the CFA part. So the rules for identification for the structural model. Rule number 1 is that your degrees of freedom must be equal to or greater than 0. So in other words, you have to have a just or an over-identified model. And the way that you determine your degrees of freedom ahead of time, now when you run your model, as long as it's 0 or greater than 0, M+ will tell you what your degrees of freedom are. If it's less than 0, M+ will tell you that you have an identification issue and then you need to go back and look at your model. But we want to be able to identify these ahead of time and also understand where the degrees of freedom come through. And that happens through doing the counting rule, which I'm going to show you in the next few slides. The second rule is that between any pair of constructs, so between any pair of variables in our model, no more than one of the following can be true. X causes Y, so you have X arrow to Y arrow to X, so Y directly causes X. X and Y have correlated error terms. X and Y are correlated exogenous variables. So only one of those statements can be true. And if you follow the rules we talked about for specification and making sure that you have either a recursive or a bow-free model, you're not going to run into this issue for rule number 2. So as long as you follow the rules for specification, you're going to be good to go on rule number 2. So what we really need to worry about is rule number 1. the counting rule. So the way the counting rule works is through simple arithmetic. You're going to count things up, add them together, and subtract two things. So the first thing you're going to do is determine the number of observations. So you're going to determine how many observations you have, and there's some simple arithmetic in order to determine that. The second thing you want to do is determine the number of parameters that you have, and this you get by looking at your model and counting up the number of parameters. And then what you'll do is subtract parameters from observations. So observations minus parameters. If you get a positive number, you're over-identified. If you get a negative number, you're under-identified. If you get 0, you're just identified. That's how this works. So to determine the number of observations, you just follow the formula on here, p times p plus 1 divided by 2, where p is the number of manifest variables in your model, or the number of variables in your model. So where this number really comes from is it takes the total number of covariances and the total number of variances in your model and adds them together. Now you can get that by just doing p times p plus 1 divided by 2. So for example, if you have 5 variables in your model, you just do p, that's 5, times p plus 1, that's 6, so that gives you 30. Divide that by 2, that gives you 15. So let me show you in a covariance table what this looks like. So let's say we had a model where we have 5 variables: parental warmth, parental conflict, adolescent anxiety, adolescent depression, and adolescent alcohol use. And if we made a table where we had, this would be similar to like a correlations table. Remember that covariances is just the unstandardized version of correlations. And let's put down the covariances, so the unstandardized correlations. That's this orange triangle that you're seeing here. And then in the spot where we would normally have the dash, where we'd have nothing in there, because a variable can't be correlated with itself, we just put the actual variances of each variable. So the variance for parental warmth, for parental conflict, that's going to be on that green box, on that green triangle. And if we add these up, we'll find that there are 15 cells that have data. Those are our 15 observations that we have in our model. And if we just take 5 times 6, divide by 2, we get 15, which is the number of observations that we have. The total number of variances and covariances combined together. So the next thing you need to do is determine the number of parameters. And the way that you determine the total number of parameters is to draw out your model, make sure that you put error terms or disturbance terms for each of your endogenous variables. So everything that has an arrow going into it has an error term or disturbance on it. And then all you do is you count up. So you count up the total number of variances first, and the number of variances is counting up your exogenous variables and then each of your disturbances or error terms. Then you total up your covariances. That's going to be your double-headed curved line, so your correlations in your model. And then you add up your total number of directs. So that's all your single-headed arrows. So you count those up, add them together, and that is your total number of parameters. And then you just do observations minus parameters. So if you had 10 parameters with 5 variables, you do 15 minus 10 equals 5. You have 5 degrees of freedom. So we're going to go through a number of examples here on the next few slides to show you exactly how this works.